All right. Now let's talk a little bit about acceleration. What is acceleration? Well, acceleration is the rate at which velocity changes over time. An object accelerates if its speed or direction, or even both of these things, change. An example is a car at a stop sign. Let's say you're riding with your family and you guys are coming up to a stop sign. Well, you're accelerating in the form of deceleration because you're starting to slow down to stop at the stop sign. And as soon as you know it's clear to go, you start accelerating again to get back up to your normal speed after coming from a stop. Now you want to get back up to 30 miles per hour. So that is acceleration. And like I said, acceleration can be a change in speed, like a race car accelerating, or in direction. So like speed skating in an oval or a Ferris wheel. And these things are examples of centripetal acceleration. So they're examples of accelerating in a circle. And what is centripetal acceleration? Well, this is a uniform circular motion. So with a windmill, it's always moving in a circle. And just like our Earth is always revolving on its axis in a circle. Just like that. What would happen if after calculating our acceleration, I ended up with a positive number? Let's say positive 32. Okay, if we ended up with a positive number, that means that we're accelerating, as in we're speeding up, because we're increasing. Like this picture here. This runner is accelerating. He is speeding up. He's got a positive acceleration. If the number is negative, let's say negative 32, that means we're slowing down. We are decelerating, like this skateboarder here. Well, now let's figure out how to calculate acceleration. So the equation for calculating acceleration is A equals final velocity minus initial velocity over time. Or A equals this delta symbol. If you don't know from math class, this means change in. So A equals a change in velocity over time. And your change in velocity is just this here. And our typical units for acceleration are meters per second squared. So now let's practice. A car on the highway is traveling 55 miles an hour and it passes another car. In order to pass this car, it has to accelerate to 65 miles per hour. The car reaches this velocity 40 seconds later. What is the average acceleration of the car? So remember, our acceleration equation is acceleration equals velocity final minus velocity initial over time. So in this case, our final velocity is 65 miles per hour because that's what they needed to get up to pass their car. And their initial velocity, what they started with, the normal traveling speed, is 55 miles per hour. And it took him 40 seconds to get up to 65 miles per hour from 55. Well, first thing we notice here is that we have a unit issue. Our time is in seconds, but our speeds are in miles per hour. So let's convert our 40 seconds to hours. there is 3,600 seconds in an hour. So you're going to set 40 on the top and the first side of the box. Then to get rid of the second units, you have to divide 40,600. Time for this is going to be 0.011 hours. All right, so let's put that down here. 0.011 hours. All right, now let's do the math. Let's take 65 minus 55. Well, that gives us 10. And now let's divide that by 0.011. All right, his acceleration is 909.1 miles per hour. That is a huge acceleration. But he did increase his speed by 10 miles per hour in 40 seconds. All right, so that is how you do this. Let's try another one. So what if Marissa's car accelerates at an average rate of 2.6 meters per second? Calculate how long it takes for her car to speed up from 24.6 meters per second to 26.8 meters per second. All right, in this problem, we are given acceleration, initial, and final velocity. We are looking for time. So we need to rearrange our equation. Acceleration equals v final minus v initial over time. Well, the first thing we're going to have to do, since time is in our denominator, is multiply both sides by time. All right, and now this is what our equation looks like. But if we divide both sides by acceleration, we should have time by itself. So this is the equation that we're going to be using. All right, now let's just plug and chug. Our final velocity, because Marissa is going from 24.6 meters per second to 26.8. So our final velocity is 26.8 meters per second. Our initial is 24.6. And our acceleration is 2.6 meters per second squared. All right, let's just plug and chug now. Take 26.8 minus 24.6, and now divide that by 2.6. And you should get a time of 0.85 seconds. All right, so not only are we going to have to use the acceleration equation like normal, we are going to have to rearrange it for the different variables, just like we did with our speed equation. Now let's compare acceleration and velocity. Well, as velocity increases, so does acceleration. So this would be the case of somebody speeding up. As velocity decreases, so does acceleration. This would be slowing down. Well, when the direction changes, so does the velocity. And when there is a constant velocity, there's no acceleration. Because if there's a constant velocity, that means you're moving at one speed over a certain period of time. So let's say you're driving down Superior Street here in Duluth, and you are going 30 miles per hour for 6 blocks. Well, you're going at a constant speed of 30 miles per hour for those 6 blocks. So you're not accelerating because you're not speeding up, and you're not slowing down. Now let's look at these graphs. These are acceleration graphs. They're position versus time, just like our speed graphs. But we can take a look at these and see if whatever is moving is accelerating or not. With the first graph here, you can see this is a straight line. That means this person is moving at a constant velocity because they're going at the same speed at all times. So in this case, there would be no acceleration. The next graph here, there's a straight line. It stays at the same position for a period of time. That means in this graph, they have not moved. So again, this graph shows no acceleration. The next graph is very similar to the first one, but it's going at a negative velocity. So they're going at a constant negative velocity, which means if it's constant, there is no acceleration. With this third graph, it's got a curve that is moving towards the x-axis. So it's kind of looking like half of a parabola there. And this is showing acceleration because the speed is changing. It's not constant like with the first graph, and it ends up going faster near the end here, taking less time to go a certain distance. So there is acceleration with this graph. And the last graph. This one has a bow that is facing towards the y-axis. So this one does as well show acceleration. And this one is in the form of slowing down, because as you notice, near the end here, it's taking more time to go a smaller distance than it was with the fourth graph here. So if the line is bowing towards the x-axis, that means it's accelerating or speeding up. If it's bowing towards the y-axis, it is accelerating, but it's slowing down. So let's do a recap. The resultant velocity is the combination of two or more velocities. You add them together if they're moving in the same direction, and you add the negative if they're moving in opposite directions. Acceleration is the rate of change in velocity over time. The equation is A equals the change in velocity divided by time. If a graph is curved inward towards the x-axis, that means acceleration. If a graph is toward outward towards the y-axis, that also means acceleration. So this wraps up our lesson on resultant velocity and acceleration. If you've come up with any questions, write them down in your journal. And if you feel that there's a question that you need to be answered right away before you do the worksheet, then please send me an email, text me, and I will get back to you. Otherwise, have a great day.